Alright, welcome everybody. I hope you're enjoying this distance learning experience. I know I'm certainly not. I definitely prefer to be back in the classroom, but hopefully these videos make it a little bit easier to complete the homework. So this is the first one I've made for you guys, but this will be the third one that I've made out of all these videos, and what I'm learning is my handwriting is horrible, and my computer is too slow, and this pen is not the best either. So bear with me. It is going to get a little messy, but we'll try to be as clean as possible. Okay, in this section, we are learning a method of rewriting rational expressions called the method of partial fractions. So you can see we really only have one objective, but there are 4 distinct types of ways that this can be applied. The method of partial fractions is one of those things that we learn in college algebra, and then we never really use it again until we get to calculus. So if you don't take calculus, you'll probably not see this show up anywhere else. So that, as far as I can remember, that was really one of the only places where it had a particular use, was when you start doing integration. Integration can be quite difficult when it comes to a rational expression, and the first thing that we try is applying the method of partial fractions to rewrite the rational expression in a way that makes the integral easier to evaluate. So what do we mean by partial fractions? Well, one way to think about what we're trying to accomplish is to think about it in reverse. So up to this point, most of the time when I would give you rational expressions, you were either adding, subtracting, or multiplying them. So imagine I asked you to add these 2 rational expressions here. In order to do that, you would need to get a common denominator. Well, the common denominator can easily be found by just multiplying these 2 denominators together. So to make that happen, we would have to multiply the top and bottom of the one on the left by x plus 4, and then we would multiply the top and the bottom of the one on the right by x minus 2. Once the denominators match, then you simply add the numerators and you get the resulting sum here. The method of partial fractions is going this direction. We will start with this expression, and we want to express it as a sum of what we would consider to be more simple fractions, each fraction having a single term in its denominator. So each of these addends are called the partial fractions, and together it is the partial fraction decomposition. So we're just doing the process in reverse. This diagram just shows the same thing. When you add rational expressions, that's the opposite of what we're doing. We're doing the partial fraction decomposition, which goes in the reverse direction. And as with many things in math, when you want to do something in reverse, it's going to be trickier. So much more involved, unfortunately, than just adding them together. Just a quick reminder, when we talk about rational expressions being a proper fraction, what we mean by that is that the degree of the numerator needs to be less than the degree of the denominator. So in this example here, this is a proper fraction because the degree of the numerator is 1, the degree of the denominator is 2. These are also proper fractions. Degree of the numerator is 0, degree of the denominator is 1. Okay, so we've got a long multi-step process to do this. I'm not going to read every single thing that's in here. It's going to make more sense when we just get to the actual process. But I do want to spend some time talking about these examples. But let's start with step 1. Very first thing is, if the rational expression is not a proper fraction, if the degree of the top, degree of f in this case, is greater than the degree of the denominator, then you need to use long division. Even if their degrees are the same, you would need to do this. So we divide them out, and the division algorithm guarantees that you'll get a quotient, but that the remainder, which is also divided by the divisor, will be a proper fraction. So we'll do that step first if it's necessary. Most of the problems, this won't be necessary. Okay, so once that's done, you take the resulting proper fraction and you factor the denominator. So if this was a proper fraction, what it really means is just factor g. When you factor g, you should be able to express it completely as a product of linear factors, meaning things that look like this, or irreducible quadratic factors. So So irreducible quadratic factors are just ones that can't be factored over the integers. And you may have repeated factors. That's where these powers come in, meaning that you could have this linear factor squared or cubed, something like that. Okay, so suppose that that's already done and that you get this thing here. So in this particular example, we have two linear factors in the bottom. They are linear factors because each one has degree 1. So what you will do then is you will go ahead and break it down into its decomposition. So the way it works, if they are linear factors and they do not repeat, meaning they don't have powers or the power is 1 on each of these factors, then you simply write a variable over each of the individual factors. We typically use capital letters. It's just the convention that's most often used here. So A over the first one, B over the second one. Order does not matter. You could have had these reversed, and then just our definitions of A and B are reversed. So the idea will be you have to apply some process to figure out what the values of A and B are. Okay, so suppose that instead it has a repeated factor in the bottom. These don't repeat. Well, what would that look like? That could look something like this. This one has only one linear factor in the denominator, but it's repeated, meaning it has multiplicity 3. So what you have to do when there's a repeated factor is we do basically the same type of thing. And in this case, we're going to get 3 different partial fractions. You write A over the linear factor raised to the first power, then another variable over the linear factor squared, and then the last one, another variable over the linear factor cubed. So then again, now we're solving for the values of A, B, and C. It's possible that one or more of these is actually 0. The reason we write this as the partial fraction decomposition is the only way to have this as a denominator is if it was the sum of 3 terms that look like this. And again, one of the terms might not be there. It could just be totally missing, but these are the possible denominators that could be combined to give you a common denominator of this. Same thing up here. Right? In order for this to be the common denominator, the 2 individual fractions would have to have these as their denominator. So that's why we're breaking it down this way. Okay, let's look at the next case. So the next one is, suppose we have a quadratic factor in the bottom, irreducible quadratic. So in this example, these are 2 quadratic factors. Neither one of them can be factored over the integers. So we can't reduce them down any further. So the idea for these, they are going to be the 2 different denominators, but the numerator now is not just a single letter. It's actually its own linear factor. If we go back to the previous ones, the one way to think about this is the degree of the bottom here is 1, and the degree of the top is going to be 1 less than that, so it's going to be 0. Now it kind of gets contradicted here because you'd say, well, the degree of the bottom is actually 2, but it's a repeated factor, so we don't think about it that way. So think of it just in terms of what's in the parentheses. The degree of this is 1, the degree of that is 0. It's 1 less. When we go to the quadratic factors, the degree of the top has to be 1, since the degree of the denominator is a 2. So it gets more complicated. Now we have 4 variables to solve for, A, B, C, and D. So the ones with quadratic factors, they're not very nice. Okay, then the worst case scenario is when you have quadratic factors that actually repeat. And this follows the same pattern as the previous one, so that being your first possible partial fraction is a linear factor, just like what we had up here, divided by the quadratic factor, but then you have to have another one where you increase the power. So whatever this power is, if it was cubed, we'd have to have a third one over here with the denominator cubed. But each of the numerators are linear factors. Okay, so all of that is just to set up the problem. Then we have to use algebraic techniques to solve for them. So one of those techniques is actually solving a system of equations. We will show that most of these, though, can be solved without setting up a matrix and doing row reduction. But this is why it's included in this chapter. We just finished row reduction, and this is something that can be modeled with a matrix. All right, so let's try a problem. Okay, so one of the things things that I'm noticing as I'm writing these notes out is, man, I could probably give you guys a lot more room. So try to write small. If you're going to fit this into the notes that I gave you, this will take most of the space there in order to fit it in there. Okay, so we want to do the partial fraction decomposition for this rational expression. First thing to notice is the degree of the denominator is 3, the degree of the numerator is 4, so this is not proper. Since it's not proper, we have to go through long division. So just to save time, I've already gone through and done that. Remember the basic process is you put the divisor here, you put the dividend here, then you ask yourself, well, what do I have to multiply x cubed by to turn it into this? And the answer is you have to multiply by 2x. So we go ahead and distribute it to both of those. 2x times x cubed is 2x to the 4th. 2x times negative 4x is negative 8x squared. And it looks like I missed a square there. I just forgot to copy it down. Okay, then you subtract down. So these cancel, those cancel, and there's nothing to subtract from this, so it drops down. That's the only step that we have to do because the degree of this is now greater than this. So this is your remainder, and this is your quotient. So the way to actually write that out is you've got your quotient plus the remainder over the divisor. This is now a proper fraction. So this is what we're going to do the partial fraction decomposition on. Now, if you recall, the first step in the process was to factor that denominator. So let's try to factor x cubed minus 4x. Well, first thing, we've got an x we can pull out. Leaves us with this. X squared minus 4 is a difference of squares. So this is the factored form for that denominator. All right, so the improper fraction could be written as 5x minus 2 all divided by x times x minus 2 times x plus 2. Okay, so we can go ahead and start breaking it down. So this one's not too bad because every factor in the denominator is a linear factor and none of them repeat. They don't repeat because the exponent on each factor in the denominator is 1. So we're going to get 3 separate partial fractions. First one's going to be a over x. You just put a variable over that factor. Second one, b over x minus 2. And then c over x plus 2. Now again, the way we assigned these variables is arbitrary. Those a, b, and c could all be switched around. You will solve the problem the same way. They just have been defined differently. Okay, so the next step is we're going to multiply the denominator here by everything. So when I do that, on the left-hand side, we obviously will just get 5x minus 2. When I multiply this by this term here, the x's are going to cancel. So let's write it out. It's going to get a little bit long. Normally, you just do this part in your head, but first one, so let's write it out. All right, so then we'll go ahead and do it to the next one. And the third one. Okay, so we're going to get a lot of canceling here. In the first one, obviously the x's cancel. In the next one, the x minus 2 is going to cancel. And then in the final one, the x plus 2's cancel. All right, so let's write down what's left here. So we've got 5x minus 2 equals a times x minus 2 times x plus 2 plus b times x plus 2 plus c times x minus 2. Okay, now the idea is that this equation should be true for any value of x. The left-hand side has to equal the right-hand side. So we're going to pick values of x that are convenient to us to help us solve for a, b, and c. You can technically pick any value and plug it in to get a new equation, but if you conveniently choose the values of x, we'll be able to quickly solve for a, b, and c. And the basic idea is this. If I could wipe out a and b simultaneously, I'd be able to solve for c. So the question is, what value of x would wipe out both of these? Well, they both have this factor of x plus 2. So if I plug in x minus 2 into this entire equation, these are going to get wiped out. So let's actually just do that. All right, so when I plug in negative 2 to the left-hand side, we're going to get negative 12, it looks like. Then on the right-hand side, we're going to get, okay, so we plug it into this, we have a times negative 4 times 0. And normally we won't even write this out because that's just going to get wiped out. Then for this term, you get b times negative 2 times 0. Again, wiped out. Then c times negative 2 times negative 4. All right, so what we end up with is negative 12 equals 8c. And then divide over, you get c is equal to negative 12 over 8, which is negative 4, I'm sorry, not negative 4/3. Each one is divisible by 4, so divide top and bottom by 4, you get negative 3/2. All right, so there you go, we have c. So now we can do this same type of trick. I'm going to try to fit it in, actually let's scroll down. Okay, so we got our value c. We want to now find the values of a and b. So we just do the same type of process again, picking a value of x that's convenient, one that will wipe out the other variables. So notice if we do x equal 2, it's going to wipe out a and c. Let's do x equals 2. All right, left-hand side, you're going to get 10 minus 2, which is 8. Then you'll have a times 0. I'm just going to abbreviate this time, plus b times 2 times 4, and then plus this times c times 0. Right, that's going to get wiped out because of that factor there. All right, so that leaves 8 equals 8b. You divide over, you get b is equal to 1. All right, now we're just left to find one more. So the last choice is obviously to use x equals 0. It's going to wipe out these two and help us solve for a. So x equals 0. On the left-hand side, you're just going to get negative 2 when you plug 0 into this. Then a times negative 2 times positive 2, plugging 0 in here, plus b times 0 plus c times 0. So those just get wiped out, and we're left with negative 2 equals negative 4a. Divide this over, and we get a equals positive 1/2. So we have the value of c, we have b, and we have a. And you could have solved for these in any order, right? Doesn't matter, I could have plugged in any of these values in any order. Okay, so if we go back to the original setup, we said that it had the partial fraction decomposition has to have this form. So let's actually grab that. sit. That was a little loud. I guess we need to make this smaller. It probably would have been faster to rewrite it now. Okay. So what we need to do is come back and just plug in each of our values. So the decomposition is 1/2 over x plus 1 over x minus 2. I'm getting some slowdown here. Plus negative 3/2 over x plus 2. Okay, so I don't like this compound fraction stuff. Fractions within fractions is not good. So we need to simplify this. So ideally, you can do this in your head. If not, you're going to need to write it off to the side. So that first one says 1/2 divided by x, which is the same as 1/2 times 1 over x. All right, I'm going to pause real quick, see if I can't get rid of this lag. I'll be right back. Okay, CPU seemed to have cooled down, so... Alright, so multiply these, you get 1 over 2x. It's jumping back up. Okay, so that first one is 1 over 2x. Second one does not need to be changed. And then the last one, if you do the same process, is going to be, let's just put the negative out in front of it. Put the negative here, it'll be 3 over 2 times x plus 2. Okay, now you might think that this should be the answer, but remember that the original problem wasn't just this. If we go all the way back, we just did the decomposition of this, so to finish it, we need to have a 2x out in front of the whole thing. So the original problem, which was 2x to the 4th minus 8x squared. Oh boy. Plus 5x minus 2. All divided by x cubed minus 4x. That decomposition is 2x plus all of this. Alright, so there we go. It's a long process, and unfortunately, this is kind of the easiest type. They get much messier than this. Okay, so I'm going to pause again, and I'll be right back to start the second one. Alright, I'm back. Hopefully we don't keep getting the lag, but it doesn't look good right now. Okay, so the next one. This is different from the previous one because it has a repeated factor in the denominator. Now, nice thing about it is we don't have to factor it. We don't have to do long division because it is a proper fraction. So we can go ahead and start writing down what it should look like. Alright, so we know first one is just going to be a simple fraction with the linear factor in the denominator, variable above. The next one, we have to do power 1 higher because it's a repeated factor, and then we have to do a third one as well. So this is the decomposition. For each repeated factor, meaning for each multiplicity, you have to have a fraction of increasing power on each of those. Okay, so again, next step is we're going to multiply each term by this denominator. So what we will get is 2x, and then when you multiply this by the x minus 1 cubed, one of the factors will cancel. So that's what would be left. Right? This multiplied by this fraction cancels one of those factors, but leaves a square on the top. Then middle one, and then the final one, it all cancels. You just get c there. Okay, so we're going to do the same game again. We want to try to plug in numbers that are convenient, numbers that will wipe things out here, and the only good possibility is 1. So when we plug in 1, the left-hand side is 2, and then these are going to get wiped out. A times 0 plus b times 0 plus c. So those are gone. We immediately have the value of c. Now for the other ones, we don't have any good choices, so we're just going to have to pick another number. So let's pick something that's at least easy to evaluate. So let's do x equals 0. All right, so if we plug in 0, left-hand side, plugging into this one, we get 0. And then you will have a times negative 1 squared, plugging 0 into this. B times negative 1 plus c. We simplify this. And then here, where I have the c, I already know that c is 2. So I can actually replace that with 2. So we get an equation that just has 2 variables. So let's put this in standard form, meaning we're going to move the negative 2 to the other side. So this really says a minus b equals negative 2. Can't do anything else with this, but when we pick another value here, we will get a second equation with a and b in it, and so then we can solve that linear system. So you can pick whatever you want. Let's go with negative 1. You have to be careful picking negatives, because that's usually where mistakes are made, but hopefully we'll be careful here. So left-hand side is negative 2, then it will be a. If I put negative 2 into this, or sorry, negative 1 into this, I will have negative 2 squared. Then b times negative 2 plus c. So if we clean this up, right, and again, c, still, it's 2, so we can put that back in. So I can subtract that over. I get negative 4 equals 4a minus 2b. And everything here is divisible by 2, so we might as well just go ahead and divide it. So we've got negative 2 equals 2a minus b. So together, with that equation and this equation, we have a system that we can solve. So let's try putting that up here. 2 by 2 system, elimination will work easily. So we're going to subtract the 2 equations to make the b's cancel. So we will get negative a equals 0. So that means a is actually 0. Divide both sides by a negative, you get a is actually 0 there. Okay, so once you have a, you can find b by just plugging back into the equation like we normally do. So we have 0 minus b equals negative 2, which just says b is 2. Okay, so now we have all the values. We have our a, b, and c. So we can write out our final answer. So we have 2x over x minus 1 cubed. The first one I really don't need to write because it's going to get wiped out. so we'll skip that one. Then we have 2 over x minus 1 squared plus the c, which was 2. Both of them were 2. So this is our partial fraction decomposition. So as with many of our problems, you can check your answer. You would just have to go through the process of actually adding these together and simplifying, and it should turn into this expression over here. Okay. All right, let's move on to the next example. So we've done partial fractions with just linear factors in the denominator. We just did an example with linear factors that were repeated. So now we have one that has a quadratic factor and a linear factor. Neither one are repeated because their exponents on the outside are all 1s. This is an example of it is proper because the degree of the top is 2, the overall degree of the bottom is 3, so we don't have to do long division. So we can go ahead and put it in its form. Let me actually stick that here so I don't have to rewrite this. So it's going to start off with a over x plus 1. Right, the degree of the top is 1 less than the degree of the bottom. The second one, though, since the denominator is quadratic, and also notice this quadratic cannot be factored, because if it could be, we do need to do that. But since this is quadratic, the numerator will have to be a linear factor. So this is what the breakdown will look like. Okay, so then the first step is the same as always. We're going to take this denominator, and we're going to multiply it by each of these fractions. Technically, everything's getting multiplied by this. So the left-hand side is just the numerator, x squared plus 3x minus 1. When I multiply this by its denominator, just cancels it. Then we will have a times x squared plus 2, because when I multiply this by that fraction, the x plus 1s are going to cancel, plus the bx plus c, which has to be in parentheses now. When it gets multiplied by this, the x squared plus 2s are going to cancel, so it's multiplied by x plus 1. Okay, and now we go through the same process again. So we have one obvious value to choose, which is going to be -1. So let's start with that. And again, negative numbers, be careful. So when I plug it into this, I'm going to have a positive 1, because -1 squared is positive, -3 minus 1. We'll simplify that later. When I plug it in here, we're going to have a times 1 plus 2. And here you're going to have negative b plus c times 0. So this gets wiped out. That 0 kills that whole thing. Over here, we're going to get just -3, and then we have 3a. So a is -1. Okay, so that was the obvious choice. The next one that we should give a try is 0, because 0 is going to wipe out the b. Do that. All right, left-hand side, you're just going to get -1. Then it'll be a times 2 when we plug 0 in here, plus b times 0, which wipes out, plus c times 1. Okay, so -1 equals 2a plus c is our equation, but we already know a, so we can plug that in. So -1 equals -2 plus c. Add this over, and you get c is equal to 1. All right, so we've got the a, b, and c. let's keep going right here so we don't have to scroll. We want to be able to keep this in our view. So we have to pick another value again. Doesn't matter what number it is. Let's just pick 1. Easy to compute with. So if I plug 1 into the left-hand side, we're going to get 1 plus 3 minus 1. And the other side is a times, not 3. The result is 3, but 1 plus 2 plus b plus c times 2. All right, then we get 3 on the left, and 3a plus 2b plus 2c. And we can go ahead and plug in our values for a and c then. So 3 equals negative 3 plus 2b plus 2. All right, so we get this. Add it over. 4 equals 2b. And then divide. B comes out as 2. All right, so we've got the 3 values, which enables us to come back here and we can write out what the final answer actually is. It should be negative 1 over x plus 1 plus, we've got 2x plus 1 over x squared plus 2. And that is our partial fraction decomposition. Okay, so this approach is probably the preferred one, but once you start getting into quadratic factors, specifically the ones that repeat, this method can get to be pretty painful. So there is another approach that is used, so I want to illustrate it here. I only use it when the problems get particularly messy, like the next one, but I think it would be helpful to illustrate it here. So let me erase some of the things that are here. Okay, so what the method does is it says go ahead and expand all of this out on the right. Kind of a mess, but let's go ahead and just do that. Right, over here we have to FOIL. So first, outer, inner, and last. So the first term is bx squared, then plus bx, then cx, and then plus c. Okay, the next thing we're going to do is put all the terms together that have the same degree and factor that term out. So for example, if I put these next to each other, I could pull out an x squared. So it would look like a plus b times x squared. Then these two terms go together. So b plus c, pull out the x. And then the final terms plus 2a plus c. Nothing to pull out on those. We could say you're pulling out a 1, but it should look like this. Now, how is this useful? This doesn't look like we've done anything useful. Well, let me bring this back down here, and I'm going to write it with the coefficient in front of the x squared. Remember that these are supposed to be equal no matter what, meaning for any value of x. Well, the only way that this quadratic can equal this quadratic is if each coefficient matches the coefficients here. So what we mean by that is a plus b has to be 1. For these to be the same, that coefficient has to be a 1. Similarly, the coefficient of the x has to be 3. So b plus c has to be 3. And then finally, this constant has to be equal to that. So 2a plus c has to equal -1. So what you end up with here is a system of 3 equations with 3 unknowns. You could write this system as a matrix. It would be 1, 1, 0, a solution of 1, 0, 1, 1 with a solution of 3, and 2, 0, 1, -1. And then if you solved this system, either row reduction or Cramer's rule, if we do row reduction, you can check this on your calculator if you want, but it reduces the row reduction gives you this as your solution matrix. And notice that is saying A is -1, which is what we had, B is 2, and C comes out to 1. So there are problems where this process is actually cleaner, and we're going to see one of those on the next, I believe it's the next one. Yeah. So this one is particularly messy. So hopefully there aren't too many of these. I think they're mostly going to be on homework 2. But I think the method I just illustrated is probably the best way to do this one. It's still not going to be pretty, no matter which way we do it. You know, definitely leave yourself a lot of room. We might have to continue this one on the back of the page as well. Okay, so what should its decomposition look like? It's already proper, so we don't have to do any long division. But this one has repeated quadratic factors, which is why it is not nice. Okay, so your first factor is going to be a linear factor, because that's quadratic on the bottom. But it's repeated, so we have to do a second one. And then we have to handle this one as well. That one we can just do a single letter. So that's what the form of that partial fraction decomposition has to look like. Next step is the same as all the other ones. Take the denominator, multiply it by each of the terms. So that will look like this. All right, when I multiply this by that factor, one of these cancels, but you still have one left over. And we have this x minus 1 as well. This multiplied by that, only one of those x squared plus 1's cancel. Okay, so then the next one, it's going to cancel this completely, leaving just x minus 1. And then multiply this by the last one, and you have just this. So just the x minus 1's cancel. Okay, at this point, you have two options. You can just start plugging numbers in, but you're going to have to plug in a lot of them. So there are a total of, what do we have here, 5 variables. You will have to plug in at least 5 numbers in order to solve for all the variables. And, you know, it might work fine. It might be the fastest way to do it. But I do think for this example, it is probably easier to expand this whole thing out. Now, I will take advantage, like if you have an easy factor, I would probably go ahead and take advantage of that. So let's do that one, and then we'll start expanding it out. So let's do x equals 1, which gives us 2 equals a plus c times 2 times 0. So that whole thing is gone. Plus b plus d times 0. That's all gone. Plus e times, this is going to be 2 squared. So what you end up with is 2 equals 4e. So e equals 1/2. You don't have to do this step here, but it will be probably helpful later. So let's come back to this now, and we're going to start expanding it out. And hopefully I can fit all of this up here. Scroll down a bit. Okay, so my recommendation would be to FOIL this one. I would leave the one with the letters out until the end, so we'll FOIL these two, we'll FOIL this, and we have to FOIL this. Alright, so we will get x cubed minus x squared plus x minus 1. And maybe rather than have you sit here and watch me do all this really slowly, I'm going to pause it, finish foiling these, and then have you join me again. Okay, so when I started expanding this, I immediately recognized something that you are probably all wondering since the very beginning of the problem. Why did I skip B here? I have no idea. I'm not sure what was going on in my head. It doesn't matter. Maybe it's confusing for you, but I should have gone A, B, C, D. But for some reason, my brain chose not to do that. So that part won't match the book if you look at it, but it doesn't matter. We'll get the same final answer in the end. Okay, so I have gone ahead and expanded these, and I also plugged in the 1/2. We said E was 1/2, so I put it in and distributed to those terms. Okay, so next I'm going to expand this. So we'll just distribute the AX through all of them and then distribute the C through all of them. So again, I'm going to pause you, have you join me back in a second. Alright, we're back. It's all fully expanded now. So the next thing that we need to do is look at each term and group it together with a term of the same degree. So if we start with the 4th degree, there's only 2 terms. So what that will look like will be, we can pull the x to the 4th out, so it says a plus 1/2 times x to the 4th. And then we go through and we do the same thing with all the other powers. So the next one we've got negative ax cubed plus a c, and looks like that is it for the x cubed. Move on to the squares. So we have a, we have minus c, plus b, plus 1. All right, then the x terms, negative a plus c minus b plus d and then lastly the constants. So terms without variables looks like minus c plus d minus d. And plus 1/2. Okay, so after all of this, what has this done for us? Well, remember that all of that is supposed to equal this. So this big 4th degree polynomial has to actually just be equal to that. In other words, this has to be 0 because there is no x to the 4th term over here. Let's scroll this down. Okay, so because there is no x to the 4th term, a plus 1/2 has to be 0. Which means we immediately know that a is actually negative 1/2. Then we go on to the next one. There's no cubic term here either. So negative a plus c has to be 0. But we just found a. A was negative 1/2. So this really says 1/2 plus c is 0. So c is negative 1/2. I just set off Siri. Hopefully the mic doesn't pick that up. Okay, so we got the c. All right, move on to the next term. Still, no x squared term here. So this whole thing has to be 0. And we have the a, we have the c. We'll be able to solve that for b. So negative 1/2 plus 1/2, which just means those are going to wipe each other out, plus b, we're going to go ahead and move this over, equals negative 1. So b equals negative 1. Getting a lot of lag again. All right, so we have the value of b. Okay, a, c, b, move on to the next one. Now this one, we do have an x term up here. So this expression's not 0, it's actually equal to 2. So negative a plus c minus b plus d equals 2. All right, so if we plug all of our stuff into this, we've got 1/2 minus 1/2 plus 1 plus d equals 2. Okay, so these cancel, subtract this over, and we get d is equal to 1. All right, and I believe that is everything now, because we had e all the way back here. We've got the a, b, c, and d. Okay, so we need to just go back and put all of those things into this expression. So I'm going to pause it so that you don't have to painstakingly watch me write this, and then we'll come back here. Okay, so I just copied this down here again, plugged in all the values that we have solved for, and so we're basically done, but we want to clean this up. So I don't want fractions within fractions. So the easy way to do this without doing keep, change, flip is just multiply the top by 2 and the bottom by 2. It will clear out the fractions, and we're really only multiplying by the value of 1 when we do this. So that works on the first one and the last one. So we end up with, as our final solution, and there we have it. Just distributing the 2's in the tops, and I would just leave them out as coefficients in the bottom. There's no reason to distribute them. So this gives us our final solution. Yes, it is a nasty process. But, I don't know, it's still kind of satisfying the fact that it works out. So hopefully you don't get too many nasty ones like this. If you are having trouble, make sure you do email me, let me know, and I'll try to help you out where I can. So again, apologize for the messy handwriting. I'm not sure how I can improve this. The performance on my laptop is really bad, and when it starts to lag, it gets really hard to write it all. So hopefully we can get this to work better, but good luck, and we'll see you at the next one.